This is ME401 at Clarkson University, and this is the bistable compliant mechanism fatigue testing group.
We've run into a problem with traditional multi-part ski bindings. Over time, they become loose, fatigued, and they can break. We're testing compliant mechanisms for the application of a ski binding to see if it would be a better option. We're testing the material properties of different 3D printer materials. Woo! Another backflip!
My name's Trevor Reese. My name's Josh Pillow.
My name's Riley Box,
My name is Jacob Tonovitz.
and this is our compliant mechanism fatigue testing group.
For our test, we're asking the key question: can a 3D printed bistable compliant mechanism perform well in fatigue tests, and which material works best in similar high cycle environments to that of a heel of a ski binding? The objective of our test is to analyze the fatigue and deformation of a bistable compliant mechanism after 10,000 cycles while varying the material and comparing the material properties for real-world applications of a ski binding. The drawing you see on screen is the mechanism we're using for our test, which can also be seen right here. That's how it works. A compliant mechanism is a mechanism that is one solid part. It uses elastic deformation to switch between positions, and our mechanism is bistable, meaning it has two stable positions. So this is our compliant mechanism. It's in one stable position right now. It's stuck right there. Elastic deformation occurs at these joints, and it flips to the other stable position where it stays there. Like a real world example of a bistable compliant mechanism is like a goldfish box seen on screen. It like flips open, it locks open so you can pour your goldfish out, and then it locks closed again and keeps it closed. The reason we think a bistable compliant mechanism would be good for the heel of a ski binding is because it reduces part costs and just makes the design very simple. It would be a lot cheaper of a product, and there'd be a lot less points to fail. Cycling these switches 10,000 times because that's the expected lifespan of a ski binding. Each switch we're testing is a different material, and we're studying the material properties and seeing how they do in high cycle environments.
So in order to test these switches 10,000 cycles, we need to build a fatigue tester. So we used our resources here at Clarkson, including the makerspace and other resources and materials available here in the Mechie lab to build this, our fatigue tester. How this works is we have a stepper motor here that drives two cams that are linked to this guide rail here. This here is our load cell, which is going to record the force that is induced through the switch. And this black switch here is what we're actually testing. We're going to be able to switch these switches out for the different materials that we used and get the data for all of them. Now here we have our circuit, which we built. First we used an Arduino Maker 1010 Wi-Fi to control our code and run both our stepper motor and record our data from our load cell. This is a load cell signal amplifier, which takes the signal from the load cell and makes it so that the Arduino can actually read it. And over here we have our stepper motor driver, which takes our higher voltage power from our adjustable power source over here and puts that into the stepper motor and tells it how many turns to go and how fast to go. Now, in order to control all of this, we wrote a code using C++ and uploaded it to the Arduino through our computer, and then we built a dashboard in order to control everything and see what's going on in live time as we run the test. So over here, this is our dashboard. First, we have our cycle count, which you can see here is a bar chart that goes up to 10,000 cycles as it runs. And then we have both a forward fraction and a backward fraction force. Now, how we are graphing and calculating these forces is we're having a cycle period of 5 cycles when it first starts, where it's going to take the highest forward force to flip it forward and the highest back actuation force. And we're going to graph everything as a fraction. So all readings from then on will be graphed as that reading over that initial peak value. And so that allows us to easily compare the graphs between all the different switches, so we don't have to worry about scaling the magnitude of the forces that they used. Now, when we hit run, we can see that it works pretty well here, switches the switch back and forth. Nice and close too.
Just mute this, right?
Yeah.
Then I have to now.
And if you look over here, you can see the readings are popping out, and we're getting our forward force fraction and our back force fraction, and our cycle count is increasing. Now, as far as the different materials that we're going to be testing, we have a TPU, just a standard 95A, to represent like a really ductile, long-lasting, durable switch. We have a polypropylene switch, which is a bit stiffer, has a nice stiff switch action, and hopefully it'll last a bit longer. We also have a PET-G, which is our super stiff, really rigid, brittle one. We have a nylon, which is also pretty stiff, but a little more ductile than the PET-G. And then we also have a special material treatment that we're gonna do to the PET-G. This is Weldon. This is a acrylic cement that's gonna act as a localized plasticizer. So we're gonna use this bottle and this needle here to apply it to the joints where there's lots of bending and motion to increase the ductility in that specific location, which will hopefully increase the lifespan of the switch. So here's an itemized list of everything that we use to build both our fatigue tester and print out the switches and test them. Stepper motor, the load cell and the signal amplifier, the guide rail that provided nice linear motion, the bearings, the Arduino, the stepper motor driver, the breadboard and the jumper wire kit, which we use to wire everything together and connect the circuit, the adjustable power source, the 3D printed base and cam parts, and the various 3D printing filaments. The total cost we ended up being $187.25. And you can see here we have the cost tabulated up on the right. We did get a lot of our items directly from the lab or filaments from the makerspace, so we didn't have to pay for that. So that was really nice. And then here's our schedule, which walks through the entire semester that we use to purchase and obtain testing instruments, to confirm the testing filaments, to write the test plan, to plan everything out, and then build the mechanism, build the fatigue tester, print out all the switches, and run all those tests, and then analyze the data and write the final paper.
There's been a few other tests done doing high cycle testing and fatigue testing on bistable compliant mechanisms, but those tests were more focused on designing the actual switch to work better for high cycle environments. Our test is different because it focuses on the material properties, specifically that from a 3D printer. Doing this test poses a few hazards. While not too significant, they still needed to be accounted for. So there's a lot of moving parts in our project. You could be pinched very easily by this, or something could break and snap and go in your eye. So that's why we're wearing safety glasses. You're also not supposed to touch the test bench while it's running to avoid pinches. The electrical components also pose hazards. They can heat up, short. You could get shocked even though it's low voltage, so it's not very high risk, but it could heat up and burn you, so it's very easy to unplug the power source and step away if you need to. The biggest risk was the weld-on. We applied this to some of the joints and the switches to increase ductility. We used this little dropper with a needle to very carefully apply to the precise places we wanted to. We made sure to wear gloves and safety glasses to avoid risks of skin damage or getting in your eye.
All right, so we completed all of our testing for all the different material switches. As you can see in these graphs here, this is what output from the Arduino onto the computer. Just a lot of data points, and we graphed it. So these graphs are the number of cycles versus the actuation force, which basically measures over time how much they deform and how much weaker they get, the switches. And as you can see, the materials produce different results as expected. The TPU and the polypropylene ended up doing very well over the full 10,000 cycles. And the PET-G ended up snapping about 1,500 cycles in. And the PET-G with weld-on made it a little longer, but didn't last the whole 10,000 either. And the nylon lasted about 6,000 cycles. And yeah. It's also worth mentioning that the peak actuation force is, you can see it's out of 1 and -1. That's because it's out of the fraction. As Riley mentioned earlier, the first 5 flips measure the peak actuation force at the start, and then we just use a fraction throughout all of our testing to see how it compares.
I would say even.
All right, so after we got some data from our original testing, we decided to dive into the material properties of some of the materials we tested. And two of the main trends we saw in the material properties from ductility and Young's modulus. And the ductility is basically how much a material deforms before it fully fractures. And the Young's modulus is how resistant a material is to bending and stretching. And so we realized that for ductility, you really want to be in a range between like 400 and 800. We kind of narrowed it down to probably 500 or 600% because that is going to be elastic enough for the material to last that many cycles. And as you can see, the nylon and the PETG are pretty low ductility, so they didn't perform very well. That's just one trend we noticed. And then for the Young's modulus, you want to have a relatively low Young's modulus. As you can see, the TPU and the polypropylene were pretty low. But the reason the TPU wasn't super ideal is because it was super flimsy and it wasn't super stable in both the bistable positions. And the polypropylene was almost too stable and it snapped too quick, which was its demise and ended up hurting it long run. And then we also did a little bit of analysis on the degradation rate. And this was basically a calculation. We took a linear regression of the graphs you previously saw on the last slide, and we took the slope of that and multiplied it by 1,000. And that basically gave us the loss in actuation force over 1,000 cycles, as you can see right there in the graph. And that basically shows us how after the break-in cycle, how quickly it's declining and how quickly it's gonna fail over a long period of time. And that helped us determine what an optimal material would be if we are going to make a ski binding.
Our main source of error came from the sensor aliasing. This error derives from differing frequency in the load cell reading and the switch activation. In simpler terms, the load cell amplifier is collecting data at 10 Hz, which is at a different frequency than the peak activation force, which is what we were looking to record. This frequency offset creates a cyclical variation in the data, which can be approximated by taking the average half height of the cyclical variation from each test. This error averaged out to 3.79%. We also see a 0.25% error from the load cell. This error is from the load cell assuming the relationship between voltage and force is linear, while in reality it is not. Some of this error also derives from manufacturing tolerances of the load cell. The last uncertainty we see is from the HX711 signal amplifier. This error comes from the noise, as when the signal is amplified, error is introduced due to some random fluctuations caused by scaling imperfections. On our graphs, we see some small fluctuations like random spikes or drops in the recorded data. These are caused by small bumps or vibrations, as when we did the experiment, it was in an apartment where like you're bumping into tables and whatnot. After analyzing the data, we found that polypropylene and the TPU filament perform the best. This is due to their high ductility percentages that are around 400 to 600%, and their lower than average Young's moduluses that range from 0.6 to 0.8 gigapascals. This allows the material to be flexible and malleable, which is optimal for a cyclic life cycle. The biggest takeaway from this experiment is that we can use the results to interpolate data of material properties to find the best fit material to use for ski bindings. Our uncertainty analysis is relatively low, allowing us to determine that our large-scale trends are statistically significant. This has to be taken with a grain of salt, though, as we didn't perform any repeatability tests, so there could be fluctuations due to print quality or environmental factors. In order to perform this experiment, we had to make our assumptions. Our first assumption was that the cycle frequency was low enough where there would not be deformation due to heating, and we assumed that this frequency was constant. Our other assumption is that the 3D filament materials were homogeneous, but they were most likely not, which would be not ideal for applying this idea to an actual ski binding. This experiment tested the material properties for a bistable mechanism, but for actual application, there would need to be a substantial amount of testing on the design of the mechanism. With further research and experimentation, a longer lasting and more affordable ski binding could be possible in the future. We want to thank Clarkson University for financial support, Dr. Hoover for facilitating and providing materials and feedback while going through this whole process, and we want to thank the Makerspace for performing all of the 3D prints in a timely manner. Thank you.
My name's Trevor Reese, and this is our rap song.
I'm living in a world of compliance. No rigid joints. One piece wonder, yeah, that's the main point.